All right, here we are. A little bit of a longer chapter today. Critical thinking done. There they all are. Moving on to chapter 4. Let's get to it. Chapter 4, energy and matter. All right, number 1. The blank system is the modern version of the metric system. That's going to be SI. You can find that on page 53. SI stands for Système International de Unidas. You can just remember it as the international system or system of international. I believe that might be French. So this is the modern version of the metric system. So remember that. Right here, number 2. The two main classifications of energy are, I went with potential and kinetic, D. I got that on page 54, and this was page 53. 3. The law of conservation of energy states that all the above, which is energy can be changed from one form to another. It cannot be created and it cannot be destroyed. So I went D, all the above. That's on page 54. Number 4, the weight of a substance is defined as the blank force of gravity acting on the substance. A, that's on page 54. Number 5, the density of a substance is defined as the mass of the substance blank. I went divided by its volume. Now in the book, it says pounds over cubic feet. So pounds would be, weight, cubic feet, volume. And then I just Googled it just in case, because sometimes the things are worded in a way I don't 100% understand. I want to make sure that I'm using the right terminology. And Google says density equals mass over volume, pounds mass, cubic feet, volume. So, all right, that was on page 54. All right, number 6. 1 second. If a substance has a specific gravity less than 1.0, it means that the substance is C less than water. That's on page 55. Now, when it comes to specific gravity, it's the amount of so when we take a volume of a liquid or a solid and we take the same amount of water, you find out what the density is. So if it has a higher specific gravity than 1, then it's going to be a more dense item. And if it has less, then it's going to be less dense than water, and therefore it may be more buoyant. Now, I did spend an extra couple of minutes just Googling it, just trying to understand the difference between specific gravity and relative density, and they are being used interchangeably, although there is a difference. And the closest difference I got is that specific gravity uses solids and liquids and an equal amount of water, and relative density is usually involving gas, and they use hydrogen. So specific gravity, solids and liquid, equal amount of water, relative density, same amount of gas to hydrogen to find out density or buoyancy. But ask your teacher. Some of these chapters, they weren't assigned as homework, so I'm doing them outside, and they haven't been graded. A lot of these were not assigned for homework. But this is a crucial chapter, this energy and matter, because it's going to come up every single class. All right, objects that float, number 7. Objects that float on water have a specific gravity less than 1. Specific gravity less than 1. Once again, if it's below 1, it's going to be more buoyant than water. Water is going to be heavier or more dense. So I got D, that's on page 55. 8. Relative density is defined as the ratio of the mass of a certain volume of gas. Certain volume of gas is compared to the mass of an equal volume of hydrogen. Knowing this concept, that density is mass per volume, a heavy gas would then have a relative density B greater than 1, page 55. All right, moving on. And the reason why it would have a relative greater than 1, because it's a heavy gas. It's heavier, so it's going to be, in a sense, more dense, less buoyant, even though gases aren't buoyant, but you know what I'm saying. Or they could be. I could do more research on that, but not right now. Blank is the rate at which work is performed. That's going to be power. So number 9, the answer is power. That's on page 56. Force kind of looks like the answer, but it's not, because force is the energy applied to matter. That's on page 55. But the answer for number 9 is C, power, and that's on page 56. 10. Temperatures. Temperatures measured on the Planck scale can be converted to Fahrenheit temperatures by subtracting 460 degrees Fahrenheit. Upon looking at it, I'm like Kelvin, but nope, I read a little more. Obviously, page 58, and it's the Rankine. Oh, I didn't write it. It's the Rankine. So page 58 is D Rankine. So when you see Rankine, think minus 460 degrees Fahrenheit. When you see Kelvin, think 273 Celsius. So 0 degrees Rankine is negative 460 degrees Fahrenheit. And when you think, okay, I can show you just a little. Let me show you a little. And when you see Kelvin, it's 273 degrees Celsius, okay? So the answer for number 10 is D, Rankine, page 58. 11, so I do all the work on the paper. I just start with the paper and I complete everything on the book, but I don't want to show the book too much because I don't want no problems. And then a lot of times I recopy the answer, the couple of answers on the page and go from there. 11, the blank of a substance is the amount of heat added or released to change the blank of a substance is the amount of heat added or released to change the temperature 1 pound of a substance by 1 degrees Fahrenheit or 1 kilogram of substance by 1 K. The answer for that is that I put is D, specific heat capacity. That's on page 59. And when it comes to specific heat capacity, there's something you remember is 1 by 1. 1 pound by 1 degree. That kept coming up. What's specific heat capacity? Change in temperature of each pound by 1 degree. 1 by 1, 1 by 1, pound by degree, Fahrenheit. All right, we're on number 12. Enthalpy is the blank. That's going to be D, total amount of heat. When you think enthalpy, think total amount of heat, and it goes on D, total amount of heat in a substance calculated from an accepted reference point. So total amount of heat by reference point. Total amount of heat, just keep, that's on page 62. Number 13, blank is the method by which heat is transferred from one substance to another through a circulating medium such as air or water. That's going to be B. I drew some pictures down here. That's going to be B, convection, on page 63. Now, if we look at this, so the big three that we're talking about in this chapter, we got conduction, we got convection, and we got radiation. So we just did convection. Whenever I hear convection, I think hot air, because I think they also make convection ovens, and they like blow heat to cook and stuff like that. So convection, I automatically think air. So sort of like here, there's a heater in your basement. The heater then sends forced air through the rest of the house, and you feel the heat. Much like putting a pot on there. Let me see. Because usually when it comes to convection, it's going to be gas and liquids, gas and liquids. Conduction is going to be all three, solid, gas, and liquids. So let me start over here. Conduction. Conduction is going to be solids, gas, and liquids. Convection is just going to be gas and liquids. And then radiation is just going to be electromagnetic waves. We'll talk about that last. So for conduction, basically, let's say you were going to go into Mordor and you were going to fight Sauron. You're going to go to fight the Eye of Sauron right here. You put your sword, you're getting ready, you tell the elves, I need a nice sword. They take the sword, they put in, I don't know, is that a kiln or whatever? They put it in there. When you put the sword in here, right, the handle's not in the fire right now. This part is. But the fire will heat up the sword to the point where this handle will eventually get hot without the fire actually coming in contact with it, because it's come in contact with what's connected to it. That's conduction. Much like if you were to sit down on a heating pad, that's conduction. You're sitting directly on something and it's transferring into your body. Conduction, direct physical contact. Convection is through air, where the only physical contact is the air. That is the medium. So the heat is actually here and it's being transferred through the air to you, heating your house. Air, convection, air heat, just think air heat. Last one is going to be radiation. So the sun is all those millions of miles away, if not billions of miles away, and it's heating our earth. But here's the thing, everything in between the sun and the earth, it's a vacuum. There's really no temperature change. But somehow the heat can go from here and then end up here. That's radiation, electromagnetic waves, sunlight, infrared. Here's Superman, he's absorbing, you know what I'm saying? But here's the thing. This is hot. Now you're warm, but so is everything in between you. This pipe, the area around the pipe is all getting warmer. Here, nothing here is really getting warm. It's a vacuum. Same thing here. This is warm, and this just becomes less warm because this is the direct heat. So this will still get hot. So this will be hottest, hot, warm, hottest, hot, warm, but it's all connected. There's no missing piece. Radiation is the only one that has that missing piece in between, where the heat source and then the heat target. Vacuum in between, no medium. All right, move it on. All right, cool. Number 13 is B, convection, page 63. Number 14, heat energy can be categorized as latent heat and sensible heat. I went with that. That's on page 64, talking about latent heat and sensible heat. Latent heat is a change of state with no change in temperature. Sensible heat is change in temperature of a substance. All right, so I have this image. This is what we used in school, something very identical to this. So if you look at this, you can, let me turn it this way. Oh, it's not doing that. Go sideways. There you go. All right, so sensible heat is simple. You're looking at a thermometer. As the temperature goes up and down, that's all sensible heat. It's every single increment of change, half an increment, everything you can put your hand on sensible. You can sense it, you can touch it. That's all sensible heat. Latent heat is very specific areas. It's these two areas right here. So as the ice melts and turns into liquid, there's a section there where the temperature isn't changing. It's at that one specific degree, right as it's about to turn into a liquid, where there's a latent heat, where basically the temperature is remaining exactly the same, but the state is starting to change. And then as the temperature continues to rise, it does it one more time when it goes from liquid to gas. So this whole thing is all sensible, no matter how high or low you go. But only at these specific points, 1 and 2 right here, latent heat of fusion, latent heat of vaporization, does latent heat really matter. And it's that perfect precision, and this is HVAC from the student's point of view. Understanding how to make this happen. Because refrigerants, they do it at different temperatures, and that's part of it. So you're like a scientist. So that's when so sensible heat, up and down, all the way. Latent is just these two, from solid to liquid, and in reverse, liquid to solid, and liquid to gas, and gas to liquid. All right. Let me continue on. I think, cool. So number 14, number 14 is sensible heat, D, page 64. Number 15, latent heat is added. Latent heat is added to a substance that causes a substance to change state. We just talked about that. Latent heat is when it goes from gas to liquid, liquid to gas, solid to liquid, liquid to solid. That's latent heat, is the change. Sensible heat is just a change in temperature. So you can change in temperature, and regardless of it's just I'm not gonna, I don't want to repeat, but just go back, because you get what I'm saying. So every increment up and down, that's sensible. When the increment stays the same temperature wise, but the state changes, that's latent. All right, 16. A ton of refrigeration effect is defined as the amount of heat absorbed when a ton of ice melts during one 24-hour day, page 66. So when you see ton of refrigerant, that's 1 ton of ice. How long it takes 1 ton of ice to melt in 24 hours. So ton of ice, 24 hours. Ton of ice, 24 hours, because that's going to come up a lot, especially with BTUs, British thermal units. All right, we're on to the critical thinking. critical thinking, chapter 4, number 1. This is going to be, if you go over to page 60, there's a chart, but you don't need too much from that chart because they gave you the answer for the specific heat capacity. But there's a chart there for specific heat capacity on everything, including glass. But for this question, the question is, calculate the amount of heat in BTUs needed to raise the temperature of 2.5 pounds of glass from 45 degrees to 350 degrees Fahrenheit. The specific heat capacity of glass is 0.187 A. BTU pounds Fahrenheit. Show your calculations. Now it threw me off because they said glass, and I thought as it, but regardless, these are your numbers that you got to focus on. You only care about the word if you're going to use the chart, but you don't need the chart. That's on page 60 because it's right here. So they gave us our 2.5 pounds. They told us the material. They told us the specific heat capacity. They told us the temperatures. So at this point, this is the equation, and this is on page 60. Directly next to the chart, they break down examples. So you can input your numbers and match them up according to the formula that is given. So the formula starts, I'm putting my 2.5 pounds here. I'm putting my 0.187, which is my specific heat capacity of glass. And then in parentheses, I'm gonna put the temperatures. Now, every single formula I saw, the big number goes first. It doesn't matter which way they're going. And I looked at all the equations. It doesn't matter if they're going from 354, they always put the big number, whether it's going to or fro, first. I'm assuming it's because they can't have a negative, because if they switch this here to here, you would have a negative 305. And I think that would mess with the equation. They always put the big number first. Check with your teacher. So just like kind of like PEMDAS, parentheses, exclamation, multiplication, division, addition, and subtraction, you're going to start with the parentheses. So you're going to subtract this, get 305. That's number 1. You do that first. Then you come over to this pair, and you're going to multiply the 2.5 times the 0.187. That's number 2. So you multiply these two numbers, you get 0.4675 BTUs Fahrenheit. This is just 305 degrees Fahrenheit. So they were both Fahrenheit too. They were both Fahrenheit. So right here, you see 2.5 pounds. And right here, the measurement of this is BTUs, pounds Fahrenheit. But if you notice, pounds gets dropped off on both of them. So this is now just 0.4675 BTUs Fahrenheit. Pounds gets removed, this gets removed. Fahrenheit stays the same. Okay? BTU slash pounds Fahrenheit. Pounds gets removed, pounds gets removed. The new measurement is BTUs Fahrenheit for this number that we multiplied to get here. We subtracted this to get this. We bring them down. We then multiply this number times this number. These are the two pairs. The result from these two, the result from these two, multiply them. The change in heat is 142.5875 BTU. Now we drop the Fahrenheit. BTU, British thermal units. 0.4675 BTU Fahrenheit times 305 degrees Fahrenheit gets 142.5875 BTUs. That's number 3, final. Change in heat. That's just the symbol, the triangle with the Q. All right, chapter 4, number 2. Let me read this to you. The answer's at the bottom. You just have to pick which one. Which of the following has more total enthalpy? 3 kilograms of 20% of salt brine at 65 degrees Celsius, or 5 kilograms of 20% salt brine at 50 degrees Celsius, assuming 0 enthalpy at 0 degrees Celsius. The specific heat capacity of 20% salt brine is 3.56 kilojoules, kilograms Celsius. Show your calculations. All right, so I split it. They're giving you 2 separate equations. Now, the last one, they gave you 2 different temperatures, and they asked you to find the difference. So this is the one that you might want to ask your teacher. This is what I did. They gave you 65 and they gave you 50, so I made 2 separate equations. So normally, just like before, there was 2 Fahrenheits to subtract, and you got 1 degree. This is now Celsius because they're using kilograms. Kilograms and Celsius go together. So in the last one, they gave you for a different problem. These 2 you subtract them and you got 1 temperature. So they're only giving 1 temperature on 2 different equations. So I was confused. So only thing I was like, let me just do 2 separate ones. So I took the 3 kilograms from the first section. The salt brine, they already told you what the the specific heat capacity, and they said it was the same because they're both 20% salt brine. I couldn't find any chart for 20% salt brine, so I'm assuming just because they gave it, that's the number, and there's no further research that needs to be done about that. So I just plugged that into the same equation, almost similar to the last one we had. No, stop that. Let me put this phone in. So the 3 kilograms, just like kind of the similar before, I put in the 3 kilograms here instead of pounds. There's 2 examples. They do a pounds one, and it's the same equation. It's just you're just changing the measurement. It doesn't really affect the mathematics because the equations are the same as long as these numbers. So you got the 3 kilograms. The 20% doesn't really go in here. I think they just said it, just kind of just like the last one said glass, but they gave you the specific heat capacity. It's kind of like an extra detail at this point because they already gave you what you need. 3 kilograms times 3.56 kilojoules, kilogram Celsius. That goes here. The temperature they gave to us. I didn't put this in pendollars in it because there isn't to subtract. I'm assuming that this is just what we're using. So because this is done, this is the pair that I'm gonna work at. I already have the temperature. So I'm gonna pair these two up according to the formula, and I get 10.68, the kilograms and the specific heat capacity. 10.68 kilojoules Celsius. You see how we dropped off the kilograms? Right here, we're just gonna bring that down, 65 degrees Celsius, and now I'm gonna multiply this, 10.68 kilojoules Celsius times 65 degrees Celsius. I'm gonna get change in heat, 694.2 kilojoules. I'm gonna do the same thing over here. Kilogram salt brine, 20% at 50 degrees Celsius, 5 kilograms times the same specific heat capacity, get the 17.8, and then I multiply it by the 50 degrees Celsius kilojoule. So this number gives me the 17.8 kilojoules Celsius. I'm multiplying it by the number, 50 degrees Celsius, and then it equals 890. So the answer, in my opinion, would be this one because that has a greater enthalpy, and enthalpy is the total amount of heat. And that's page 61 through 62. All right, so the last one is actually easier out of those 3 critical questions. An air conditioner for a single family residence has a capacity of 1,008,000 BTUs per day. Calculate the tonnage. How many tons of refrigerant is designed to handle? Show your calculations. All right, so this one is on page 67 to 66, 67. They already tells you what the BTUs were for the day. So what you're gonna come down here, and on page 66, there's an equation, and it tells you, because you know this, you can skip kind of the first half. So because you know this part stays the same, 24 hours and 12,000 BTUs. This stays the same. The only thing you're adding is this, the 1,008,000 BTUs into 24 hours. And that right there, that's the first part, you get 42,000. So if you were, 24 goes into that 42,000 times. And if you wanted to recheck your answer, you would just multiply 42 times 24 and you'll get 1 million. But moving forward, you're gonna divide this by this, 1,008,000 by 24, you're gonna get 42,000, and that's gonna be BTUs an hour, which means every hour, 42,000 BTUs are being used. And at the end of 24 hours, 1,008,000 will be used. The 12 is just coming down. We're just carrying it down. And if you look, BTUs an hour, now we have the same metrics. So all that is a simple division. You get 3.5. 12 is here, so now you're dividing that into that. Actually, no, you would divide this by this. So you would type in this first into your calculator, divide by 12, 3.5 tons of refrigerant effect. That is everything. Divide, get this number, bring this number down, divide by this, get this number.